With my great pleasure and big honor, let me introduce our next speaker today, Volodymyr Nekrashevych from Texas and A&M University from USA, who will tell us about self-similar inverse semigroups. Volodymyr, you are welcome.
Дякую. Зараз я включу свій. Мені не дозволяє. Тепер дозволяє. Okay. Thank you for giving me this opportunity. I'm very happy to give this talk, this conference. So I talked a lot in recent years about self-similar groups and their relation to dynamics. Today I will talk about one generalization. I will tell later why this is useful. So groups are used to describe symmetries of structures, and inverse semigroups are useful when you want to describe partial symmetries, so symmetries between parts of structure. And there are many structures which have many partial symmetries but don't have globally defined symmetries. So self-similarity in this case, so similar groups act usually on set of words over some alphabet. Here we can consider a more general setting of acting not on all words, but on some set of words. So let X be a finite alphabet, and the full one-sided shift as a space is the space of all infinite one-sided sequences with coordinate-wise convergence topology or direct product topology. And on this space, we can define the shift, which just removes the first letter. The shift itself will not play much role in my talk, but it's important that there is this dynamical system in the background. So a topological Markov chain is defined by a set of words of length 2, some subset, and we take all sequences in X omega such that every two neighboring letters taken together, so every subword of length 2 is in this set T. So this set T is called the set of admissible transitions. And so we say which transitions are allowed and take all such sequences. And this is invariant under the shift. So if a sequence satisfies this condition, then its shift satisfies the condition. So we also get an map sigma on that Markov chain. So for example, a nice case is when you have a directed graph. So you have some vertices and some arrows going between the vertices. And you take all sequences of edges of arrows in that direction. So all infinite paths as sequences of arrows, of edges. So that will be an example, actually a typical example of a Markov chain, a topological Markov chain. You can take sequence of vertices given by this chain, but or sequence of edges, both of them are topological Markov chains. So in general, topological Markov chains are just ways to encode something more general called subshift of finite type, and even more, not more general, but purely topologically, you can define a subshift of finite type as any dynamical system, so a map, where F is a compact, totally disconnected space, metrizable or metric space, and this map sigma is open, so image of open set is open, and expansive. Expansive means that there is some delta such that if 2 points are on distance less than delta for all iterations, then they're equal. So any two different points can be taken apart, delta apart by the map sigma. One can show that every such a map is topologically conjugate to a topological Markov chain or shift. Namely, one can encode points of f as sequences when we fix some Markov partition of the space. And Markov partition is a partition of the space into clopen, so compact and closed and open subsets, such that if you take any element of the Markov partition and apply sigma, you get a union of elements of the partition. Then, if you take a point of the space, you can write its itinerary. So write in which, well, here it must be n, in which set your point is at every moment. So that sequence which describes the trajectory. If the partition elements of the partition have diameter less than delta, then this sequence will uniquely define the point x. So you can encode points of the space by these sequences, and this will be a Markov partition. Markov chain, topological Markov chain. Okay, so that's the setting, the space on which self-similar group acts. They act on self-similar inverse semigroups act. They act on Markov chains. Okay, so what are self-similar semigroups? So let's take some topological Markov chain and consider this map, which writes a letter x to the beginning of a word. Note that this map is not defined everywhere. So we look at it as a map on SF, because for some sequences W, XW is not in F. So then this is not defined. So it's a partial map. And it's a homomorphism. So it takes some subset of F, set of those sequences for which you can write X at the beginning, and maps it to space of sequences starting with X. So it's a partial homomorphism. When I say partial homomorphism, I mean homomorphism between clopen subsets, so closed and open subsets. So a collection of homomorphisms between clopen subsets is said to be self-similar if for every element of that set and for every letter, this composition, you do Sx and then F, can be written as a disjoint union of these compositions. So writing X at the beginning of the word and then applying an element of the set, F, is the same as first applying some element Fi to W and then writing some element Xi. So you can push through F through letters. So if you know what self-similar groups are, you see that it's similar. The difference is that for self-similar groups, you act on the whole space X omega, not just on the Markov shift. And it's not a disjoint union, it's one element. So Fsx is equal to some Sy, so F prime. So that's what happens for self-similar groups. In the case of inverse semigroups, you have partial maps and you have this disjoint union. Sometimes it is convenient to work in an algebra and then write this disjoint union as a sum, in the so-called Steinberg algebras of inverse semigroups. And then this will be some kind of relation in an algebra where it says that you can always write a product F times Sx as sum of products Sxi Fi. Okay, I'll give you examples a little bit later. So we say that inverse semigroup is self-similar if it is a self-similar. If it is a self-similar set in this sense, it is equivalent to the condition to be generated by a self-similar set. So if you have a self-similar generating set, then the semigroup generated by it will be also self-similar in this sense. Okay, another definition which is sometimes useful is that the set is self-similar if every element, if for every element and every pair of letters, when you take this transformation, so you take Sx, then apply F, and they take Sy inverse, so you erase Y, this transformation, which will be partial homomorphism, is either empty or is an element of A. Or you can add empty element as zero into A, and then you don't have to mention that either or, just an element of A, if you include zero in the set A. So this is also similar to something that some of you may know from self-similar groups. In self-similar groups, there's a notion of a section of an element. And that section is exactly this S G of X inverse G S X. You don't have to write two letters because S Y is uniquely defined by F and X in the case of group actions. But in case of semigroups, this Y is not uniquely determined by F and X. So like here, if you have F and X, you can have different cases, not only one case. There's one difference. But still, you can consider self-similar inverse semigroups as you can describe them using automata. So you can construct something called Moore diagram. So you take vertices to be your transformations. And whenever you have a non-empty transformation Sy inverse F Sx, so that's all will be also an element. If it is not empty, will be also an element of the set A. And you draw an arrow and label it by X and Y, meaning that if F is applied to a sequence that starts with X, it transforms X to Y and then acts on the remaining part by this element of A. And then if you have infinite directed path starting in the vertex F and labeled by these pairs of labels x1, y1, x2, y2, and so on, then it will mean that if you apply F to x1, x2, and so on, you will get y1, y2, and so on. Again, this is the same as in the case of groups. One big difference is that you may have one vertex, so a state of your automaton, and you have two arrows, both labeled by X, and then you have one y1 and then another y2. And so if you want to act on finite words, you don't know where to go. You are in the state F, you read X and the input, and you don't know either y1 or y2. But if you take an infinite sequence, there will be unique paths for that infinite sequence, x1, x2, and so on. And then you will know where the infinite sequence is transformed to by F. So there is action on infinite words. There is no action on finite words in this case. Okay, now an important class which appears in dynamics naturally is the class of contracting self-similar semigroups. So self-similar inverse semigroups is called contracting if there is a finite subset which includes the empty, which includes the zero, so the empty homomorphism, such that for any element of the semigroup, there exists some n, such that if you take this composition, SVF SU inverse, where SV is again the same kind of transformation, but for words V is a word, not a letter. So this element must belong to this finite set for all U and V finite words of length greater or equal to n. Again, this might be empty. So, so if you this describes action of V on tails of sequences starting with V's F. So when F starts with V, X on a word starting with V, W, then it will be equal to this if everything here is defined. So it means that self-similar inverse semigroups is contracting if, when you look at the action on the tails of words, after you erase beginnings of length n, what you see are elements of some fixed finite set n. And that finite set is called nucleus of the of the semigroup. Again, this is exactly the same as in case of groups, with some difference. The main difference is that actions are partial, and there is some non-deterministic situation. I will give you examples in a minute. So they appear naturally in something called solenoids, so hyperbolic homomorphisms with totally disconnected stable direction or unstable direction. I will not go into detail about this. I will just give you two examples, and maybe I'll mention where these homomorphisms come from. Okay, so let me give you one, maybe simplest, but not non-trivial example. Well, maybe not simplest, but simplest, nice example. So let's take the golden mean. So this number 5. So main property is that phi squared is 5 plus 1. And let's consider the circle, R mod Z. And let's take the rotation, x goes to x plus phi. By the way, phi inverse is phi minus 1. So on the circle rotation, x goes to x plus phi is exactly the same as x goes to x plus phi inverse. This is the same map. Because we are looking at the circle, it's mod 1. So now we will transform our circle into a Cantor set. So if you take orbit of, so any point in this ring, of course, mod is integers, so on the circle, which is the same as orbit of 0 under the action on the rotation, and replaced by two copies, x plus 0 and x minus 0. So basically, for example, you take starting from 0. So instead of looking at the circle, you look at the interval, 0, 1. Then there is phi inverse here. You split your interval into two subintervals. Then you have 2 phi inverse somewhere. You split that. So you continue splitting this and take the order topology. You'll get a Cantor set. So get a Cantor set, which I'll denote F. And then because we split along a set which is invariant under the rotation will induce a homomorphism on this set. So it will be a rotation of the set. Sometimes this is called the Danjois map or Danjois construction. So now let's consider an expanding map. So let's take the map which multiplies numbers on the circle, which multiplies numbers by phi. Well, it's not well defined, because if you take on the circle, if you take multiplication by phi, then x is the same as x plus 1. That's the same point on the circle. But phi x is not the same as phi times x plus 1. So these two numbers are different. So this map multiplication by phi is not 1-to-1. So let's make it 1-to-1 by choosing some branches. So let's take multiplication by phi on the interval from 0 to phi inverse, and multiplication by phi, but with subtracting 1 on this interval. So this interval will be mapped by sigma to 0, 1. And this interval, when you multiply by phi, you get 1 phi. And then when you subtract 1, you'll get 0 phi minus 1, but phi minus 1 is the same as phi inverse. So this is a continuous map on this Cantor set. Remember that these two intervals are actually closed and open in the Cantor set. Then actually, this is a shift of finite type because it's expansive. It multiplies distances by phi locally, and it's open, obviously. So it's a shift of finite type. And as I explained a second ago, this is a Markov partition because sigma of I0 is everything. So it's I0, the first interval union I1. And I checked that sigma of I1 is I0. So this is a Markov partition. So you can encode points of this Cantor set by their itineraries with respect to this Markov partition, and we'll get this way we'll identify this Cantor set with a space of all sequences of zeros and ones in which we do not see 1, 1. So admissible transitions are 0, 1, 0, 0, 1, 1, 0. 1, 1 is not allowed. This is actually very natural encoding. Namely, if you take a sequence in this space and just take this series, then you get the corresponding point in the circle. So this encoding is exactly encoding of points with this numeration system. So you get some numeration system with base phi, golden mean numeration system. And this is for numeration system for reals, for the points of the circle. You can extend it to reals also. So you'll get like a binary numeration system, but in this case, it's not binary, it's golden mean numeration system. That's what this encoding is. Okay, so let's go back to the rotation. This rotation is a homomorphism of the Cantor set, but you can restrict it to Clopin sets and get partial homomorphisms. For example, if you take rotation, then rotation transforms I0 into, so you get, remember that adding phi is the same as adding phi inverse, so I0 goes to, well, 2 phi inverse. What is 2 phi inverse? 2 phi inverse is 2 phi minus 1. Well, you probably have to subtract 2 phi. Yeah, you have to subtract 2. Anyway, so you can restrict it to Clopin sets, and you get an inverse semigroup. So this is an analog of kind of analog of something called adding machine. So if you take binary numeration system, there is an associated self-similar action called adding machine, and it corresponds to, same way as here, it corresponds to adding 1 to a dyadic integer. Here we add phi, or phi inverse, to a real given in the golden mean numeration system, or Fibonacci numeration system. So here is the automaton on the nucleus. It will be contracting, and this is the nucleus. So let me comment on it a little bit. Of that inverse semigroup. So this is the Fibonacci or golden mean adding machine. So the rotation is split in 2 parts. So there is one partial map and the other partial map. So R0 and R1, they are disjoint, and if you take their union, that's the rotation. That's the rotation x goes to x plus phi. And R0 star is the inverse of R0, R1 star is the inverse of R1. And these two are idempotent. So this is just identity on the whole space. And this is identity map, but only on I0, defined on I0, on this interval. And then, for example, now if you have a real number written in this golden mean numeration system, you take this infinite sequence and you want to know what is x plus phi as a point of the circle. You just look for a sequence. For example, we see from this that if you take R1 and apply it to 1, 0, 1, 0, 1, 0, 1, 0, we will get 0, 1, 0, 1, 0, 1. It's a homework problem for you to find out what is this number, what are these numbers, and what did I say? Or if you take 0, 1, and then 0, 0, 0, 0, 0, 1, and then all zeros, then we get 0, 0, we just get all zeros, and so on. And another interesting thing is that this is an automaton. It defines uniquely these transformations, but there is no action of finite words. If you start here, for example, well, let's start here, R1 inverse, and you get 0, you don't know where to go. either here or here, because both cases 0 is the first letter. But when you go here, then the next word that you can read is only 0, 1, 0. You can read only 0, 1, 0. If you go here, you can read only 0, 0, 0. So if you know the whole infinite word, you will know where you should go. But if you read only one letter, you don't know where to go. So it's kind of non-deterministic on finite words, but deterministic on infinite words automaton. Okay, I don't have much time. Let me just describe one more example. So we take, it's related to Penrose styling. So we take this triangle with angles 72, 72, and what we get, 140, 36. And then take a bisector here and this parallel line to the base. And let's take two transformations. One is, well, one transformation. Let's switch these two triangles, but by an orientation reverting maps. And let's just flip this triangle. Then there is transformation B, which flips this triangle, and transformation C, which flips this triangle. And then transformation D, just symmetry, which flips this triangle across its axis. Now I will define A1. A1 is this transformation restricted to this triangle. So that's the map which takes this triangle and maps it over here, flipping it. A0 is its inverse, and A2 is symmetry of this triangle. So we have these transformations, and I will not explain how you encode the points of this triangle by sequences. So it's similar to what we had with the circle. We also transform it into a Cantor set by cutting it into some sets. And here, well, let me explain it. So S0, the map appending 0, it takes the whole triangle and maps it to this subtriangle. S1 maps it, the whole triangle, to this subtriangle, and S2 takes this triangle and maps it to this subtriangle. And either by orientation reverting or orientation preserving transformations, in the case of 0 and 2, it's orientation preserving. In the case of S1, it's orientation reverting. So then these transformations will be defined by this automaton. They will generate a self-similar inverse semigroup, and this is the transformation. So again, these two are idempotent, so they define identity maps. A1, A0 are here, A2 is here, and then there are B and C and D. So remember, D is the symmetry of the triangle. B and C are symmetries of these two subtriangles, and A is a little bit more complicated. So these transformations, A, B, C, D, can be also interpreted as the procedure of moving from one tile to a next in a Penrose styling. So there is something called, I don't have time to go into detail, but if you take Penrose styling, you can consider the space of tiles of a Penrose styling. And that space of tiles is a Cantor set. And then if you start from a tile and decided to go to its neighbor, you can go either to the neighbor across the side labeled by B, or across the side labeled by A, or across the side labeled by D. Same here, A, C, D. So you get a transformation. For every tile, you get its neighbor. And those transformations are exactly these transformations. And that's one of the ways to arrange them into an action on a Cantor set, or on a triangle in this case. And this will be the automaton. So why this is used, where this is used, for instance, one can construct groups using inverse semigroups. So suppose you have an inverse semigroup of partial homomorphisms. You can take the so-called topological full group, so the group of all homomorphisms of X, so everywhere defined homomorphisms from X to X, which are unions or restrictions of the elements of G to clopin sets. So you cut elements of G into pieces and then reassemble them back to homomorphisms of X. Looks very complicated, but surprisingly, in the two examples that I explained to you, in both cases, the full group is finitely generated and virtually simple. So they have simple commutator subgroup. And something else can be proved about these groups and the proofs use inverse semigroups. So use inverse semigroup to understand the group. So for instance, one can show that the full group of the first example is amenable, which follows from a theorem by Kate Yushchenko and Nicolas Monod. It's not finitely presented. One can prove that there are no finite set of defining relations. For the second example, which seems to be more complicated, it's an open question if that group, so the full group of that semigroup, is amenable, and it's also an open question if it is finitely presented. So we don't know much, almost nothing. We don't know anything about it. We know only this fact that it's finitely presented to virtually simple. We don't know if it has free subgroups or not. Anything like that. It's completely open. But it might be potentially a very interesting example answering some questions, some open questions. Okay, that's all what I wanted to talk about today. Thank you for your attention.